Hello, calculus fans! Remember a while back we talked about the fundamental theorem of calculus, specifically for line integrals. And in order to use that to compute the line integral of a vector field, that vector field must be conservative. In other words, there has to be a scalar field f, which is called a potential function, such that del f is equal to the vector field capital F. Now, trying to check this by hand it's kind of tricky, and we don't really have a foolproof way of doing it. What we'd like is to find a way to check a vector field to see if it's conservative without looking for a potential function. So first, let's state and prove a theorem. If f is a function of three variables that has continuous second-order partial derivatives, then the curl of the gradient of f is the zero vector. Let's prove this now. Okay, so here's how the proof goes. If you compute the curl of the gradient, then it's all going to look like this. I don't want to go through all the details here, but one of the things that you're going to see in here as you go through the calculation is that you get terms that look like this, and that's just going to be zero because you're computing two second-order partial derivatives of the same function, but just computing the derivatives in opposite order. So all of these things come out to zero. And if you'll remember, we have a theorem that says that exactly that thing happens. So it all comes out to zero because when we compute second-order partial derivatives, it doesn't matter what order we compute the derivatives. That's what Clairaut's theorem told us. So we can rephrase this theorem. We'll write it like this. If f is conservative, then the curl of f is equal to zero. So what this does is it gives us a way of verifying that a vector field is not conservative. So knowing that if f is conservative, then the curl of f is equal to zero, tells us that if the curl of f is not equal to zero, then f is not conservative, because we have an if-then statement, and that's logically equivalent to its contrapositive. So let's do an example. Let's show that this vector field is not conservative. So instead of trying to prove that we can't find a potential function, instead we're going to compute the curl. So the curl of f looks like this. This is how we set it up as a determinant. Then this is what the components are going to look like. Now remember, all we're trying to do is prove that this curl is not equal to zero. Now the first component is equal to zero. We get 2x squared yz minus 2x squared yz. That's zero. But now the second component is not zero. It's 2xyz minus 2xy squared z. So what you should see here is that this piece is not zero, which means I don't even care about this last component. It doesn't matter. In order for this whole thing to come out to zero, each component would have to come out to zero. So this is an I don't care. That's why I put a squiggle there. It doesn't matter what this is. So the whole thing is not the zero vector. So we've established that the curl of the vector field is non-zero, so the vector field f is not conservative. Now if you take the original statement, which was if f is conservative, then the curl of f is zero, the converse of that statement is not true in general. The converse is to say if the curl of f is equal to zero, then f is conservative. But it is true under one additional condition. The vector field f has to be defined on a domain that is what's called simply connected. So this is sort of a complicated concept to deal with. We're not going to mess around with this very much. In fact, if the vector field is defined everywhere, that works too. So here's the theorem, which is the converse of what we just talked about, with one additional condition. If you have a vector field defined on a simply connected subset of R3, and whose component functions have continuous partial derivatives, and, most importantly, the curl of f is equal to 0, then f is conservative. So it is mostly an if and only if statement. Now, the reason for the name curl is that the curl vector is associated with rotations. So one good interpretation of curl occurs when the vector field represents the velocity field in fluid flow. Imagine if you have a moving liquid and the vector field tells you the direction and speed of the particles moving in the liquid. Particles that are near XYZ in the fluid will tend to rotate about the axis that points in the direction of the curl of f at that point. The length of the curl vector is a measure of how quickly the particles are moving around this axis. So rapidly spinning fluid will have a larger curl vector. So here is a picture to illustrate that if you have moving particles in a fluid that are going around in a circle, then the curl vector is a vector that points perpendicular to the plane of motion of the particles. And the length of the vector tells you how fast the particles are moving. There is a more precise definition. We're not going to worry about that too much here, not right now. Now, if you have a vector field whose curl is 0 at some point, then the fluid is free from rotations at that point P. So F is called irrotational at the point P. So in other words, there's no whirlpool or no eddy at the point P. If the curl of F is 0 and you placed a tiny paddle wheel in the fluid, the paddle wheel would move with the motion of the fluid, but it wouldn't spin. If the curl of F is non-zero, then the paddle wheel will rotate about its axis. Now we're going to be able to understand this concept a little bit better when we study Stokes' theorem, and that's coming up in a few sections. Okay, that's all for now.